Today's lesson involves the concept of the Taylor series. Before we go in depth on the topic and a few examples, let's talk about the history and development of the Taylor series. The discovery of the Taylor series is a controversial topic even up to this day. Although it was formally introduced by the English mathematician named Brooke Taylor in 1715, the concept was actually supposedly discovered 40 years before by a Scottish man named James Gregory. His passion for science and math led to several discoveries that are now applied in astronomy and mechanics. But due to his isolation in his late years, a few of his discoveries, including the Taylor series, are not attributed to him. As you sit down at home or during class watching this video, you may be questioning yourself, why do we need this in the real world? Chances are the Taylor series may not be an essential topic in your life, even if you're planning to major in engineering, or something of that matter, let alone in a psychology major. This is due to the fact that Taylor series are mostly applied to theoretical mathematics. Once again, you might be asking yourself, why do we need to learn this? And the answer to that question is easy. Although it's not an essential topic in your daily lives, it is an essential topic in calculus class. Therefore, if you want a good grade, you'll keep watching this video.
Before we move on to further examples, there are essential Maclaurin series which are commonly used among mathematicians. The first is 1 over 1 minus x, which is a non-altering series that is raised to both even and odd powers. The next one, e to the x, is very similar to the first one, except they are divided by the n factorial. The third series is sine x, which is an alternating series that is raised to odd powers. Finally, we have the cosine x, which is also an alternating series that is raised to only even powers.
If you consider a function in the form of the sum as n approaches infinity, c of n x minus a to the power of n with radius of convergence greater than 0, and if you want to write out the expansion for this function, it would look also like this. F of x equals z0 plus c1 x minus a squared, which would be the next term after the 0, and would keep going on from there as the function adds more terms. Then the answer would be a lot more accurate. Now if you want to plug in a certain number into this function, then f of a equals co, f prime of a equals c1, f double prime of a equals 2, and so forth. In general, we would have f to the double prime of 2 of a over 2 factorial. Have the equation of f to the nth derivative of f of a equals n factorial cn equals c to the n equals f to the power n times a over n factorial. If a problem is asking for the value of f double prime of 3, given a third degree Taylor polynomial centered at x equals 3, and would be read as follows: p3 of x equals 9 plus a times x minus 3 minus 5 times x minus 3 squared over 6 plus 19 x minus 3 to the power of 3 over 10. Then you would consider the third term, just because that would be where f double prime of x would be located. And since that term looks like f double prime of x, x minus a squared over 2 factorial, then the negative f over 6 would actually be reduced to negative f over 3, since you divide the 6 by 2. To wrap this up, the Maclaurin and Taylor series provide an accurate estimate to a certain function as the number of terms approach infinity.
Thanks for listening and watching. We hope this information was useful.